This is yet another question based on the Young's double slit interference experiment. So let us look at the question. So the question says, let the intensity on the screen at a point P in a double slit interference pattern let the intensity at that point be 60% of the maximum value. So the questions are, there are two parts. What is the minimum phase difference between the sources? These sources are basically from the two slits. Part P is, in part A, what is the corresponding path difference in the wavelength if the wavelength of light is 500 nanometers. So before proceeding, let us draw the diagram once again. So here we have the diagram for Young's double slit experiment. S1 and S2 are the two slits, or we can consider them to be two secondary sources. Here is the screen, and from the center of S1 and S2, if we draw a perpendicular onto the screen, then we consider that point as the center or the origin, and from there we will measure distance along the screen. And if we consider a point P, then we can figure out what intensity pattern is, as P varies along the screen. So this kind of an interference pattern we will see, and the screen is at a certain distance from the slits. The slits have a certain separation. So this is the setup for Young's double slit interference experiment. Now let us come to our question. According to the question, we want to find out, we are given that the intensity at this point P is 60% of the maximum value. So before proceeding, we need to know the formula for intensity. So this is the formula for intensity, where delta is the path difference, which is approximately S to M in this diagram, which is approximately d sine theta. So this is the formula that we have for intensity. I max is the maximum value of intensity. Now for 60% of maximum value, now we can solve the question. So for 60% of maximum value, we have I is equal to 0.6 times I max. So for this, we want to find out delta for this 60% is how much. So we can put it in this formula. So we will have So the max cancels out. This gives us so from this we will get that delta for 60% intensity is the following. So we can put this in a calculator. So plugging in these values gives us approximately 78.5 degrees. So this is the answer, and if you want to find it out in radians, then we divide it by pi. Sorry, we multiply it by pi and divide by 180. So in radians we will get approximately 1.37 radians. The conversion formula is 360 degrees is 2 pi radians. So 1 degree is pi over 180 radians. So our final answer is that the path difference for 60% intensity is approximately 78.5 degrees, which is approximately 1.37 radians. This solves part A. Let us now move to part B. In part B, we want to find out the phase difference. Sorry, the question I wrote wrong. This is not path difference. We want to find out the phase difference. So we want to find out the phase difference given the wavelength. So we have, first we can find out the expression for phase difference given the path difference. So phase difference is path difference into lambda over 2 pi. Sorry, I have made a mistake over here. Actually, in this part A, we were supposed to find out the phase difference, and delta is not path difference, it is phase difference. Argument of a cosine function is always in radians, so this is phase difference, not path difference. So this is phase difference. Let me correct myself. Pardon me for making a mistake in the beginning. And this is path difference. And phase difference and path difference are related. So if we have path difference, let's say delta x, the corresponding phase difference is, let's say, delta phi, then they are related as follows: that the path difference is lambda over 2 pi times the phase difference, or we can write it the other way around. The phase difference is 2 pi by lambda times the path difference, where the phase is in radians. So phase is in radians. So here we need to find out path difference only. So part A was about phase difference, part B is about path difference, and they are related as follows. So let us come back to the question. So we have the path difference is related to the phase difference as follows, and phase difference in our case is delta for 60%, and wavelength we are given is 500 nanometers. And in part A we found that phase difference is 1.37 radians approximately, so this is approximately divided by 2 pi. This gives path difference is approximately 109 nanometers. So path difference is approximately 109 nanometers. So just to recap what we did in this question was based on phase difference and path difference, and I made a mistake in the beginning between phase difference and path difference, so one needs to be extremely careful with these two terms, so please be extremely careful. Phase difference and path difference are indeed proportional to each other, and they are related as follows as given over here, but they are different. So path difference and phase difference are related with a factor of lambda over 2 pi between them, and this path difference is approximately d sine theta, and from the path difference we can find out the phase difference, or from the phase difference we can find out the path difference. So phase difference will be in degrees or radians, and when the phase difference is taken to be in radians, from that we can find out the path difference as we did over here in this question. So this is path difference. So this solves the question on Young's double slit experiment and phase and path differences.